Hey guys, it's your boy Snert. Welcome back to Elite Hacksaws. We're going to be doing the thing we always do, which is the interview preparation kit. And I figure, last video I hit you guys with the super secret techniques of dynamic programming. So I figure we'll just take it easy today. We'll do a nice simple string manipulation, and I said simple. Let's spice things up a little bit. We'll go on a nice medium problem, common child, a nice medium string problem to take our mind off of the dynamic programming. Ha! Fooled you, psych! It's actually a dynamic programming problem. So, yeah, I figure I gave you guys a basic introduction to dynamic programming. I want to solidify it now with a slightly more complex problem. So we got a definition of a child string according to this problem. So a string is a child of another string if it can be formed by deleting 0 or more characters from the other, parent string. What does that mean? Well, basically, it means what it says, right? I mean, if I got a string donkey and I got another string, I don't know, what is it going to be? DNY. DNY is a child of donkey because I can form DNY by deleting the O, the K, and the E, right? Whereas, if the string were like NDY, you couldn't do that because if you have to start with the N, so you'd have to delete the D and the O, and then there's no D following that, so you can't form NDY. So that's the idea of a substring. It's basically the characters in the child string. They have to be a subset of the characters here, and they have to appear in the same order as those characters in here. And so what this common child problem is saying to us is it's saying, okay, we're going to give you two strings, and you got to find the largest string that is a child of both A and B. So to take one of their examples there, string would be, Shin-chan and Nohara, 3 A's, I believe. Yeah. And they're saying, okay, so what is the largest common child of these two? Well, S, and so we got an H here. There's an A. I got an H, an A. Well, there's an N here. All right. So this N can match this one. So that means we shouldn't take this H, right? So we got N with N, H with H, and A with A, and then nothing else matches. So we're looking at N, H, A, so the answer would be 3. That's the size of the largest child that is common to both of these strings. And we see here, yeah, sample input 2, sample output 3, explanation, NHA. So, not that hard, not that difficult to understand of a problem. The question is, how do we actually do it? The strings, by the way, their length is going to be between 1 character and 5,000 characters. Now, one approach that you could take to this problem is, again, you could try a greedy approach. So what you could do is you could say, okay, well, I'm going to go through each level in each character in the first string, and I'm going to search for that character in the second string. So we got S. S does not exist in this string. Okay, so we skip the S. We go to the H, and we look here, and the H exists. It's the third character. So now we say, okay, so H is part of our substring. And then we look at the next character, it's an I, and there is no I after the H. And then we look for N, and there is no N after the H. There's an N before the H, but we've already taken this H. So as far as we're concerned, we can only basically consider characters after the first H in the second word. So we have to exclude this N because it would give us a bad ordering here, right? HN, which doesn't exist in the second word. And there's no C and there's no second H. And so the last one that we can take is an A. And, that would be this one here. And then an N again, there's no N after the first A. I guess the A would be here. But yeah, you get the idea. The problem with this kind of greedy approach is we ignore the possibility of skipping an opportunity to take a character in the first string. We could skip this opportunity in order to give us a better start into the second string. If we take the first character we take is the N here, then that gives us the opportunity to take this H and this A, and then we're off to the races, as it were. But the question is now, how do you decide which characters to skip and which characters to take? And that's a tricky problem. Let's consider the brute force approach. What if we just considered all possibilities of skipping and taking? How bad would that look? Well, it's pretty bad, right? So for every character, we could write an algorithm, and the algorithm would be, okay, we are going to consider, well, first of all, let's put 2 pointers, and we'll call these at the current position of each of these strings. And what we do, first we inspect this character, we say, does it exist at or after the pointer in the second string? If it doesn't, then we have no choice. We have to skip this character. We can't take it. It's impossible. Now, we would then advance the pointer in the first string. We would examine this one. We would say, okay, does this one exist after the pointer in the second string? And it does. It exists right here. So now we have 2 options from this point. We can either skip it, which means we advance the pointer here. We don't advance this pointer. Or we take it. So skip or take. And if we take it, then we add that character to our substring, and we would advance the pointer in the second string and advance the pointer in the first string. We advance both of these to just pass the H that we took. And then from each of these decisions, we would have other decisions branching off. So, in the worst case, where the characters, it probably wouldn't happen. It's not a possibility. But let's just take the worst conceivable case, where every character produces a choice between 2 options. Then obviously, your complexity is going to be big O of 2 to the n, right? So again, we are looking at exponential here. Now, of course, some of these, they're going to be skipped automatically, so they won't contribute to the 2 of the n. So this n here isn't going to be full n. Maybe it's n over 2, maybe it's n over 3 or something. But either way, that's still exponential. Now, I hope by this point this is ringing some bells, because it has a fair bit of similarity between, this problem and the problem that I showed you in the dynamic programming tutorial that was in the previous video. So let's tackle this problem from a slightly different perspective than I did last time. Let's look at our solution to the problem partway through and see if we can identify sub-problems. So what I'm saying is, let's say, we've scanned through the words here. We've reached a certain point. We've decided that we're going to take the n. So that means that our pointer is going to be here, and because we're taking the n, it's going to be here. So we take the n. Now, can we identify a subproblem? Well, yes. The subproblem now is basically, what is the largest common child between these 2 strings now? We've taken this n here, so that eliminates this and eliminates this from the 2 input strings. We have this remaining, and so we just call our solving function, our subproblem solver, on these 2 substrings now. That's the situation that we're looking for. So if we look at this now, our function is basically going to look like this. It's going to be a function of 2 parameters. In the last tutorial, our recursive function was a function of one parameter, but now we're going to have a recursive function of two parameters, string 1 and string 2, which are going to be basically, you know, ranges or sub-ranges of the input string. And here's the basic recursive formulation that I'm going to be looking at. So what we're going to do, so we have our pointers here. And before, when I was talking about this, I was basically just using string 1 as like a master, and then string 2 would just follow along as needed. It would advance as needed. But the way we're going to do it, we're going to be advancing string 1. We'll call this A and B. So we're going to be advancing A and B at the same time. So we'll have different choices. We can either advance A or advance B. Or if A and B both point to the same character, then we take that character. So the pointers at that point in the recursion, they're both pointing to a matching character, and so we can take that. We take those, is what I'm trying to say. So how does this work? If we look at our algorithm here, so we start at our root case, which is pointers are pointing to this S and this N. They're not the same. So we're either going to have to advance the A or advance the B. So we have two options, advance A or advance B. So if we advance A, it's still not pointing to the same kind of character. So now we can advance A or B, right? So let's advance A, still not pointing to the same character. So now we can advance A or B. If we advance A, in this case here, they are pointing to the same character. So what you would do in this case, you only have one choice here, and that is you take the N, you advance A, and you advance B. And in here again, they're not pointing to the same thing. So you have two options, advance A or B. So let's advance A here, pointing an H and an O. So two options, advance A or B. Let's advance B, advancing B to here. And now they match. So here you would take the H. Here you take, we took the N, the H, and so forth, so on and so forth. So this is the way the recursion would work. This is the actual, well, part of the optimum path. You'd still have to advance the A, and then the A, you get the last character, and then you just keep going until you reach the end of both strings. Actually, now that I think about it, once you reach the end of either string, that's the end of the whole recursion. So you would end that point of the recursion tree. All right, enough with the hanky-panky and the talking and the trees. Let's get on with the coding, shall we? So string S1, string S2. I mean, you know, I'm not just gonna copy these strings for no good reason. That's not in my nature. It's not in my blood. So I guess we're gonna do our using iter is equal to string const. Oh, I believe we have what do you call it? IntelliSense. That's nice. That's a nice change. All right, things are looking up. So, what are we going to do here? Well, we're going to define our recursive function that is going to return the length of the maximum common child. So that will be int, because this thing returns int, so I might as well make those match. And I don't know, max child ranges. Yeah, sure. So we're going to give it two ranges. So iter begin 1, iter begin end 1, iter begin 2, iter end. That's not, there we go. Just had to find the keys. All right. I mean, this would be nicer with, I guess, string viewer or whatever, but we don't have that technology in HackerRank, so we'll just have to learn to live without it. All right. So, this is my old style. I might as well adopt to whatever style they got here. Okay, so first things first. if we hit the end of either range, we should just return 0, right? So if B1 is equal to E1 or B2 is equal to E2, return 0. We've hit the end of one of the strings, so we're trying to find the maximum child between a string and an empty string, which is obviously going to be 0. All right, so that's basically the terminating case for the recursion. Beyond this, what are we going to do? Well, first we're going to check to see if our pointers, and we'll just use the B as the pointer in this case. We want to see if our pointers are pointing both to the same character, and if so, we want to take that. So if B1, dereferenced of course, is equal to B2, then we're going to take that. What does taking it mean? Well, that means we're going to solve the subproblem of the remaining strings after incrementing both pointers. So that means we're going to return, and because we took one character in this iteration, we're going to return 1 plus max child ranges in B1 plus plus E1, B2 plus plus E2. Now I don't think I want to do post increment there. That seems like that would be a very bad idea. So we're going to do pre-increment. Save ourselves a little debugging. But yeah, so there's the case. If our two pointers happen to be pointing to the same character, then of course we want to take that and increment them both. Now, if they're not pointing to the same character, then we have the decision, which one do we increment? Do we increment 1 or 2? And the idea is we want to recursively evaluate both of those branches in the decision tree. And after we evaluate both of them, we're going to take the maximum between them. So in that case, we want to return the maximum between the case where we increment B1 and the case where we increment B2. So I'm just going to copy and paste this. And we're not going to increment B1. We're going to increment B2. There you go. So there is our recursive formulation for this problem. And you can see that it's only when the characters under the pointers match that value will be added to the recursion. That makes sense, right? And we got our max in here just like we had in our previous problem, because many of these problems that can be solved with dynamic programming, they're going to have similarities. This is an optimization problem, very common for dynamic programming. Now, the next thing that we want to do, well, first let's actually adapt the entry point from the problem to our recursive function. So that would be return max child ranges, and then we're just going to do s1 dot begin, s1 dot end, s2 dot begin, and s2 dot end. Okay, so there we go. And this should work if I haven't messed anything up. And it should run on the small test problems and work. If it doesn't work, well, then I'm going to have to stare at the code for a little while. Okay, so it does not work. Doesn't work. So what's the problem here? All right, well, don't I feel silly. I've stared the problem down for a couple of hot minutes, and I've figured out what it is. And if you guys are interested, because this ain't a lot of code, you could even type this in if you haven't already tried to solve the problem yourself. And you could see where maybe you saw the problem at the beginning. Maybe you were screaming at the monitor, "Chili, you can't do that. Don't do it." But I did it. I'm not going to lie. So the problem is in here. So in this call to max child ranges, I want to try both options, the option of incrementing B1 and then the option of incrementing B2. So here I increment B1, call max child ranges, and here I increment B2 and call max child ranges. The only problem is that, well, it depends on which one of these gets called first. But in either case, let's just say that this one gets called first because it's easier. In this case, when this one is called, B1 is still going to be incremented, right? So I will actually be calling max child ranges here with both B1 and B2 incremented. And that's no bueno, right? So what I actually want to do is I want to call it with the next thing. And I mean, the idiomatic way of doing it, and I even, when I was typing this code out initially, I'm like, should I do it this way? And I'm figuring now, I use the plus plus because it's, you know, it's less typing. I mean, you could just use, you know, for example, B1 plus 1 and then B2 plus 1. But you know what? Let's do it the idiomatic way, which is to use the actual functions from the iterator utility library. So yeah, we want to call these functions max child ranges with next pointers in the thing, but without actually incrementing the local pointers or iterators in this procedure here. And that will make all of our stuff play nicely. Hopefully. Yes. So it is working, probably, at least for these 3 test cases here, simple test cases. So now the thing is, well, I mean, obviously, we know what's going to happen if we press submit code, right? It's going to time out. Yeah, so I mean, some of them didn't time out, probably smaller test cases. We can't see. Well, let's unlock it. Who cares? I'll pay my hackos. Yeah, you see, for small enough strings, it's going to work. But as the strings get larger, like we said, exponential runtime, we're eventually going to hit a wall. So now what's the solution? Well, like we did last time, we could basically build up the recursion from the bottom up. So we'd have to have a table, like we had a table last time. But this is going to be a little bit different because the last table, our recursive function only had a single parameter. But in our recursion this time, we have 2 parameters. So our table would actually have to be 2-dimensional. And dimensions, you could be like A or B for each of the strings. And that would be, you know, substring A is length 0, length 1, length 2, length 3, length 4, whatever. And then substring B. And this would be our dynamic programming table. We'd build it up from the bottom to the top. And then once we reach the top, that would be our answer. But today I'm going to show you guys the second approach to dynamic programming that I haven't done yet. And that is called memoization. So with memoization, basically what you do is you keep the recursive. You don't turn this recursion into a loop that loops and builds up your table. You keep the recursion, but what you do is at every level of the recursion, you know, you're going to have your parameters, you know, f of, you know, 1, 2 or whatever, f of question mark, all right? What you're going to do here is instead of just, you know, dumbly calling the recursion, you are going to keep a memoization table with the answers to all of these different f's. And whenever you call an f, the first thing you're going to do is you're going to look into your memoization table and you're going to say, have we already solved this subproblem? If so, you return that immediately and you don't go down the recursive chain. But if you haven't solved the problem yet, then you're going to go down the chain, you're going to solve the problem, and when you come back, you're going to write that answer in here so that if you encounter that problem again in the future, you don't have to solve it again, you just look it up in the memoization table. So it's very similar to the bottom-up approach. The only difference, I mean, both are going to use a table. The only difference is with the bottom-up, you're just basically explicitly looping and you're building all the answers up from the bottom, from small subproblems up until larger and larger subproblems. In this one, you're doing the recursion, you're doing top-down, you're asking the question, and then only if it doesn't exist in the table are you actually solving it. So you can think of it as, you know, eager versus lazy processing. This is the lazy processing approach. So to do this, we're going to need a table. It's going to be 2-dimensional. We could do a vector of vectors. And you know what? Before we actually jump into the code here, let's do a simple mock-up of what our table would look like for a simple input data situation here. So we've got string 1 is cat, string 2 is at. All right, so our table is going to look like this. Cat is going to correspond to the columns of our table, S1, and at, S2, will correspond to the rows of our table. So that means that we are going to need 4 columns and 3 rows. And you might say, well, we've only got 3 characters. Why do we need 4 columns here? And the answer is because what we're doing here, the addressing or the mapping of our table is going to be the length of the substring. So here can length 3, length 2, length 1, and length 0, the terminating case, will also have cells in our table. So that means that we're going to need, if we have a string of 3, we're going to need 4 columns. Or here a string of 2, we're going to need 3 rows. So that's important to understand right there. We need 1 more than the length of the string. And then we can just see what each of these rows and columns correspond to. So this column here corresponds to the case where we're using the entire S1. And then here for doing the entire S1 and A2, what is going to be the length of the largest child? That's 2, right? That's at. Here would be 1, because that's T. Cat and T, the largest child is T, common child. And null string will always have 0. So we can just write 0 in this section here. This will always be 0. And then here we have at and at. Well, that's just 2. T and at, that's 1. At and T, that's 1. T and T, that's 1. And there you go. So this is the table for each of the sub-problems here in our pair of original input strings, cat and at. And we can see it's pretty simple to understand what each of these cells, what this number means when we label it like this. And now all we need to do is how do we figure out how to, index into this. I'm going to be implementing it as just a single vector. And then we are going to index into that one-dimensional vector as a two-dimensional table. It's going to look something like this, where the order is going to be like this, traversing the cells of the table in the flat vector when we flatten it. So to do the lookup, the indexing algorithm is going to be, well, let's say that these values here are going to be I. So this would be, I1 and this would be I2. So what would it be? Well, it would be the width of the entire table. We'll call that N1 times I2 plus I1. So that's how we would index into this table here to get our values. So now that we have an idea of how we're laying this table out, its dimensions, what all the cells mean, now let's actually jump into implementing our memoization. Now there's no real need to do so, but it's my personal preference here. I am going to just write a simple class to encapsulate the memoization table and the recursive algorithm altogether. So we'll call the class common child Memoizer. And so what is it going to need? Well, it's obviously going to need, let's go private here. We're obviously going to need a vector of our values here. And what we're going to do, and we'll just call this one memory. What we're going to do is we are going to say for this vector, the value -1. So -1 means unset. So uninitialized memory. All right. So public, we need a constructor for the Memoizer that's going to set up the vector. Let's add some member variables here. Size t, so this will be n1, that's the width. Size t, n2 will be the height. And we'll do const string S1 will maintain references to the input strings S2. Okay, so with this now we can do our constructor common child Memoizer, and it is going to take in constant string S1 and constant string S2. And now we're going to initialize all the different things. So what is N1 going to be initialized to? Well, that is simply the size of S1 plus 1. The same goes for N2, and then for our S1 is just going to be referencing the S1 of the input, and our S2 is going to be referencing the S2 of the input, and there you go. Now all we need to do is actually initialize our vector. So the vector is called memory, and we want to resize it to the width times the height. So that's N1 times N2. And we want all those values to initially be -1. So we can use that with the second parameter of resize. And there you go. So now we have our table set up. Now I'd like to have a nice little function that I can use. We'll just make this private as well. So I want to have a nice little function here that I can use to index into our memory as a two-dimensional table. So we're going to do size t I1 and size t I2. And that is just going to be what I showed in the diagram, which is going to be N1 times I2 plus I1. And we want to return that, return a reference to that cell, and that will be useful to us. Now, the actual meat of things, the recursion. How are we going to do the recursion? Well, it's going to be pretty much the same as what we've been doing here. So we might as well cut this out from here, and we'll paste it into here. That doesn't change. This iterator stuff doesn't change. Now, what does change? Well, first things first, we've got to, basically we want to figure out if the answer to this sub-problem already exists in our memoization table. So how do we do this? All right, well, auto, we'll call this mem. We want to make a reference to the memory cell that corresponds to this sub-problem. And that's just at, and the length of string or substring 1, which is end minus beginning, and then the length of substring 2, which is again end minus beginning. So now we have our reference to the memory. The first thing you want to do is you want to check if mem is not equal to -1. Because if it's not -1, that means that we've already solved that problem and we just should return mem. Now, if that's not the case, then we have to solve the problem. So, I mean, if we're in the terminating case, that's easy. Set that memory cell equal to 0 and return 0. No problem there. Otherwise, we are going to want to calculate and cache the result. So instead of returning the result for when we take the character, we're going to store that in mem and then return mem. And the same idea for if we are going to be just incrementing one of the iterators to skip a character. We do mem is equal to the result, and then we return mem. And there you have it. We've implemented memoization into our original recursive algorithm. It wasn't that difficult. So now we have this recursive, and we have our at. We just need something that the outside world can call to get the ball rolling. So we'll go int go, and this is going to return, and it is just going to return a call into max child ranges over the entire original input strings. So that'll be like that. And then here, all we got to do is construct our memoization object, our memoizer. So we'll do return common child memoizer S1, S1, S2 dot go. And there you go. We've done it. This should maybe work if I haven't missed any semicolons or any other some such. All right, so the sample test cases work. Now the moment of truth. Does it work on the full-on yummy test? And it does. Everything is done. We have succeeded. Solved all the test cases. Beautiful. Beautiful. So that, my friends, is memoization. And it's the same basic idea. I mean, underlying, it's the same principles at work as the bottom-up approach. It's just, it's just like I mentioned. I've already explained it, right? It's lazy evaluation versus eager evaluation. The sub-problems are called on and calculated as needed, whereas in the bottom-up approach, you calculate each sub-problem systematically, building from the bottom up, and then once you've built all the way to the top is your answer, and you just return it immediately. So sometimes some problems might be easier to formulate as memoization. You can see here that if you already have a recursive algorithm, it's very easy to turn that into a memoized dynamic programming algorithm. So if it's very complicated, it might be easier if you've already got the recursive solution to just bolt on some memoization and call it a day. Whereas with the bottom up, you might have to rewrite it as a loop, and it might be more work. But there you go. And for the time complexity, we can see here that the number of cells that we have in our table is equal to the number of things that we have to calculate, the number of solutions we got to calculate, and that is equal to the length of string 1 times string 2. So if length of string 1 is m and string 2 is n, then it's m times n complexity. Or if they're both the same, it would be n squared. So we're looking at, basically n squared complexity here. But there you have it. Yet another example of dynamic programming. You've got our solution here. You don't need to do it as a class. I just personal preference. In this case, I don't see a big advantage in actually writing class type for this. I just like to do it. As usual, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. It helps a lot. And I will see you soon with some more coding challenges.